Okay, now here we have, good morning everyone. Now this part we are looking at belts and pulleys for the mechanics of machines. Okay, for the mechanics of machines. So in this part here we have, first we will be looking at the introduction of belt and pulleys. What is the function and the application of belt and pulleys? Usually is for power transmission. Okay, second, you have the type of belt drive, open or cross belt drive. The third, you have to look into the different belt tensions, the forces that is acting on the belts. 4, you have the ratios between the belt tensions. Then you have the power transmission or the ultimate power transmission. So these are the 5 sections we are looking at. Okay, 1, 2, 3, 4, and 5. So this is an example of a an open belt drive. An open belt drive. So you can see there is a smaller pulley and a larger pulley. So the smaller pulley here, we call it as the driver pulley. Look at my laser pointer. Okay, the driver pulley, that is the smaller pulley in gold color, and in silver, that is the larger pulley, is the driven pulley. So you have the driver and the driven. So when you refers to the belt, okay, that is lapping over both the pulley, okay, will have a tangential velocity or the tangential speed, which is when you refers to pulley 1, you will have a tangential speed of R1 omega 1, where R1 is the radius of the smaller pulley and omega 1 is the speed of the smaller pulley, which is attached or mounted on a driving shaft. So for this, we can say the shafts are in parallel shaft. So you can use belt and pulley drives here. And then on the driven pulley, you can also see that it's a tangential speed of R2 omega 2, where R2 refers to the radius of the larger pulley or the driven pulley, and omega 2 is the driven pulley speed, okay, the speed of the driven pulley. And then we have another term here which we call the center to center distance, which is X, and it is measured from the center of one pulley to the center of the other pulley. That means from the center of the driver pulley to the center of the driven pulley or the driven shaft. And then the next thing is the theta here. The theta here, we call it as the angle of lap or the angle of wrap. So when you look at this angle theta here on the larger pulley or the smaller pulley, both these must be the same based on the geometry of the diagram or the arrangement. So we call theta as the angle of lap or the angle of wrap. So how to determine the angle of wrap or lap? So from here, from the smaller pulley, as you can see, from the center of the shaft or the center of the pulley, okay, you draw a line which is represented by the radius R1 here until it touches the contact point, okay, between the driver pulley and the belt. So at this point here, you can see the belt is about to leave the pulley. That means getting away from the pulley. So that this point here to the other point here. So when the belt wrap over this section here, and the respective angle is called, or the angle is called the angle of lap or the angle of wrap. Okay, so this is, okay, a belt pulley arrangement, an open belt drives. Okay, an open belt drives. So as you can see, the smaller pulley When the smaller pulley is the driver, so when, look at my laser pointer, when the pulley exerts a pull at this point here, look at my laser pointer, please. Now, when the smaller pulley here exerts a pull at this point here, okay, at this point here, can see my laser pointer. At this point here, there will be a tight side tension on the top. That means the upper side of the belt pulley arrangement. So this side here will be tight, T-I-G-H-T. And then the belt will be delivered to the bottom side of the belt pulley arrangement. So this section here, actually the bottom part here, the belt, we say it is subjected to lesser tension, that means lesser pulling force, which we call this side here as the slack side and the upper side as the tight side. But if, let's say for example, the smaller pulley is rotating in the other direction, that means in the clockwise direction. If the smaller pulley is rotating in the clockwise direction, look at my laser pointer, okay, it will exert a pull this time at this point here. So the belt here will be subjected to tension on the lower side, that is the tight side, will be at the bottom now. So, and then it will deliver the belt to the upper side. So we call the upper side now, in this case, as the slack side. So which side of the arrangement, the upper or the lower side, as tight or slack, it depends on the direction of rotation of the driver pulley. Okay, it depends on the direction of rotation of the driver pulley. So in this case here, the pulley, the driver pulley is rotating anti-clockwise direction. So the upper side is tight, the lower side is slack. So if the driving pulley is rotating in clockwise direction, so the lower side will be tight and the upper side will be slack. So tight side tension usually is known as the maximum tension. Slack side tension is usually known as the minimum tension. And we use a symbol of T1, T subscript 1, to represent the tight side tension, and T subscript 2 to represent the tension on the slack side. Okay, now the introduction, belt or ropes are used to transmit power from one shaft to another by means of pulleys which rotate at the same speed or at different speeds. The amount of power transmitted depends upon the following factors. So how much of power transmitted, whether there is a slippage between the belt and the pulley or not, it actually depends on the following factors. 1. The velocity of the belt, okay, can actually, okay, changes the amount of power to be transmitted. 2. The tension under which the belt is placed on the pulley, the tensions, so that is your T1 and T2, tight side tension and slack side tension. The arc of contact, that means the angle of lap under which the belt is used. The greater the angle contact or the greater the angle of lap, then the greater will be the power transmitted by the belt and pulley system here. Now the conditions under which the belt is used. So it depends on where you are using this belt and pulley drives. So these are the 4 points that will greatly affect, okay, the amount of power to be transmitted. So theta is known as the angle of lap or the angle of wrapped, and okay, you can convert degree to radians by taking theta in degree divided by 180 times pi to radians. Okay, remember, you must remember when you should use theta or the angle as in radians and the angle in degree, please. Now V1 and V2, that is here, this one, look at my laser pointer, V1 and V2 here, they are the belt speed or the belt velocity, and they are given as r omega. And since there's only one belt that is lapping both the pulley, so the belt speed for both will be the same. So that means V1 and V2 should be the same because of one single belt that is over both the pulley. So V1 and V2, definitely that is to denote one as for the driver and 2 is for the driven. Okay, but V1 and V2 is the same, but R1 and omega 1 would be different. Okay, so the radius for both the pulley will be different, and the speed of the rotational speed of both the driving and the driven shaft also will be different. So since V1 and V2 is the same, so therefore you get an equation or a formula of D1 over D2 equals to N2 over N1. As you can see, D1 over D2 equals to N2 over N1. What we can say here is the speed is inversely proportional to the diameter of the pulley. So the larger the diameter of pulley, the lower the number of revolutions. That means the speed will be lower for larger diameter pulley. For smaller diameter pulley, then the speed will be higher. So that is why we write both the diameters and the speed the other way around. So if I have 1 to 2 for the diameter, then for the speed I should write it as 2 to 1. If I have 2 to 1 for the diameter, then the speed I should write it as 1 to 2. Remember, the diameter and the speed, they are inverse proportional to each other. So this is how the pulley and belt arrangement looks like. So this arrows here shows you the tangential velocity of the belt, which is equals to V equals to R omega. Now, the next part here, okay, is to teach you how to find the theta, the angle of lap. So when you refer to both the pulley here, from the smaller pulley, the center of smaller pulley, what you need to do is you need to draw a line, okay, parallel to the belt that is on top here. See my laser pointer, please. So this belt here and this line that you have drawn here must be parallel to the belt. Okay, so these two lines must be parallel to each other. And at this point A here, the line that you have drawn must touch this radius here, the radius here, which you have drawn it from the center of pulley B to the point at which the belt is leaving the pulley. Okay, so this line that you draw, here, look at the laser pointer, this line that you draw here must be 90 degrees to this line here. So you get a right angle triangle of O, A, and B. So from this right angle triangle, we know that this angle, the full angle here is theta. So half of this will be theta over 2. Half of it will be theta over 2. Okay? Follow, everyone? Now, from the diagram, we know that this is R minus R. This radius here, R, is the radius of the larger pulley. And this R here is the radius of the smaller pulley. So what is this length? If this is R and this is R, the lowercase letter r. So this difference here would be the radius of the larger pulley minus the radius of the smaller pulley. And this is half the angle of lap. And this is the distance between the center of the driver to the center of the driven pulley. Okay, we know that power is defined as force. Power is defined as the product of force and velocity. So the force we can refer to effective tension. What is effective tension? That is the difference between the tension on the tight side and the tension on the slack side. So effective tension is T1 minus T2. The velocity here you can consider as the velocity of the belt, which you can consider as V1 or either V2, which is equal to R1 omega 1 or R2 omega 2. So that is the power transmitted by the belt and pulley arrangement. Okay, so that is T1 minus T2 multiplied by the belt velocity multiplied by number of belts. The N is the number of belts. Okay, so you have this. So tight side, slack side, belt speed, and the number of belts. So for open belt drive, okay, the length of the belt. So this is the formula that we can remember, that you have to remember in order to find the length of the belt for an open belt drive. This is called an open belt drive. Later on, you will know the difference between an open belt drive and a cross belt drive. Okay, and the length, the formula here, that for the length of the belt, okay, this is minus. Remember, look at my laser pointer. This is minus for open belt. For cross belt, this should be a plus. Okay, look at my laser pointer. Can you see? Okay, so that is the formula we use for the length of belts. Okay, so this is the formula that you use to find out the angle theta or the angle of lap or angle of wrap. How do we get this formula here? So you have to refer back to the right angle triangle that is above. Okay, cosine of this angle is adjacent over hypotenuse. So the adjacent is R minus R, and the hypotenuse length is the X. So that is why you have this formula in order to find out the angle of lap or wrap if the question does not give us the theta. And remember, the theta must be converted into radians. Now the next slide here is your cross belt drive. So the same thing here. From the center of the smaller pulley, draw a line parallel to the belt here, the line of the belt, okay, and then touches with the radius or the line, which the radial line of the larger pulley. Okay, so you have another right angle triangle here. Now this time is R plus R, and this is still the X, that is the center to center distance. And this theta over 2 here is not the angle of lap actually. Okay, it's the angle that you refer to here, which is not the angle of wrap yet. So that is the length of the belt. I've told you the length of the belt for cross belt, this is plus, open belt is minus. Okay, and this is the angle of wrap. Now this time I put it as alpha. That means it wraps from this point to this point here. Okay, or when you refer to a smaller pulley, look at my laser pointer, is from this point to this here. Okay, so somewhere around here. I think that line is missing. So that would be your alpha. So how to get your alpha? So by the geometry of the figure, you must be able to know how to find alpha. So alpha is actually, okay, now here. Alpha is equal to your 360 degree minus the theta that we have found just now. Okay, now that is for flat belt and cross belt drive. Now the next thing is the centripetal or the centrifugal tension. Now since belt is continuously runs over the pulleys, therefore some centrifugal force is caused, whose effect is to increase the tension on both sides. So let's say, for example, you refer to this cross belt drive here. This side of the belt here, okay, on the side of this belt here, actually at this end here, look at my laser pointer, actually at this end here, you can consider a TC, which is acting outwards. A TC which is acting outwards. That is called the centripetal tension. So if you consider, let's say, for example, you take the mass of belt into account. If you take the mass of the belt into account, then it will definitely create a TC, that is the centripetal tension or the centrifugal tension. So bear in mind, TC only exists or appears if you were to take mass of belt into account. So if you don't consider the mass of belt, you wouldn't have considered the TC. And the next thing is, whenever the velocity of the belt is greater than 10 meters per second, then you will have to consider TC. That is the centrifugal tension, or sometimes it's known as centripetal tension. So now centrifugal or centripetal tension is given here, the formula. M is the mass of the belt, but the mass of belt here is kg over meter. The V here is the velocity of the belt. Okay, the tangential velocity, you can either use V1 or V2. So, and we know that now this mass here is not only in kg. It is kg per meter length of the belt, because the belt, as you measure, if you want to measure the mass of the belt, a belt is with its length, So if you want to measure how much is it in kg, so you must measure it with respect to 1 mm, 1 cm, or 1 meter. So that is why the mass of the belt here is expressed in terms of kg per meter. So, or you can take as density of the belt material multiplied by the cross-sectional area of the belt here. The cross-sectional area of the belt, then multiplied by the velocity to the power of 2. So this is the mass of belt in kg per meter. So rho is the density of the belt material. Now, only when mass or density of belts being taken into account, and in certain cases when the velocity of the belt is greater than 10 meters per second, then only you will take TC into account. Now, what is initial tension? Another tension here. TC is 1, T1 is tight side tension, T2 is the slack side tension, TC is the centripetal tension. Now you have the initial tension, which is denoted as T subscript O or T subscript 0. That is called the initial tension, which is also known as static tension or average tension. When we say average tension, that means T0 can be taken as T1 plus T2 over 2. Okay, so tension which is applied to the belt when it is being assembled onto the pulley. Okay, so that is your initial tension. So the next part, sorry, the slide here might be slightly long because I wanted to cover the belts in one slide itself. Okay, now flat belt, cross-sectional, you know, from here you can see, okay, it is rectangular in cross-section. So if you want to find the area of a flat belt, so you have to take the width multiplied by its thickness. And flat surface pulley. So usually for flat belt, we don't use any groove pulley. So the pulley usually is a flat surface pulley. So if, let's say, for example, you did not or you are not taking mass of belt into account, then your belt tension ratio between the tight side and the slack side, T1 is the tight side tension, T2 is the slack side tension, then it will be equals to exponential mu theta, where mu is the coefficient of friction and theta is the angle of lap. With mass, then you have to take TC into account. Then the formula for the belt tension ratio changes from this to this. Now, how you got both of these formula? Then you have to refer to your binomial series, though that is a section or in certain books they do show you the proving formulas for both of this. Now, this is for flat belt, rectangular cross section. So if, let's say, for example, you are using rope instead of belt, or using rope or circular belt, so you have a circular cross section, so the area is pi d square over 4 or pi r square, or a V belt. This is called a V belt, or even though it looks like a trapezium, but it is called the V belt. And usually circular cross-section belt or V belt, you have to use what we call V-grooved pulley. So let's say, for example, you look at this diagram here. So you can see the groove of the pulley here. This is a groove of the pulley. So, and this 2 beta here is actually, okay, denoting the groove angle. And this is your V belt that is mounted on the groove pulley. So when you refer to this, actually there are forces of R1, that is the normal reaction between this contact surface of the belt to the surface of the pulley for both sides. So that means the friction that is applied on this is twice as much as a flat belt. It's twice as much as a flat belt. So that is why for higher power transmission, it is advisable to use groove pulley with V belts, okay, or multiple groove pulleys. So without taking mass of the belt into account, then your belt tension ratio for circular belt or for V belt with groove pulley will be this. And when you take mass into account, then it changes to this, where you have to take TC into account, the centrifugal or the centripetal tension. So now this part here is for the ultimate power transmission. Now this part here I have done some proving formulas for you, but it is not necessary. But the only thing is you actually know from where the formulas arrived comes from. So the maximum power transmission, the conditions to use this. So no belt or tangential speed or pulley speed is given in the question. Second point is mass or density of the belt is being taken into account. And 3, maximum power transmitted required. If the question asks for ultimate or the greatest power transmission, without these 2 points here, then you don't need to use the following formulas. That means in order to use the following formulas below, you must have all these 3 points here in the question. So if it is, then you have to use both of these formula here. To find TC, you have to use T1 divided by 3. To find Vmax, that means the maximum belt speed, you must use this formula. That is only for the greatest power transmission, and if questions, okay, has these 3 points fulfilled. Okay, thank you very much. This is the end of the slide, and please subscribe and view. Thank you. Like.